scattering time. So that looks quite familiar, but we can do the same thing for a hole now. We'll look m star hole, v dot equals plus e plus v cross v minus m star hole velocity over tau hole. Okay? So it looks exactly the same as the dynamics of an electron, except it's charged backwards. It's a positive charge carrier. Now, if you remember way back to the beginning of the term, we had this issue with the sign of the Hall coefficient. The sign of the Hall coefficient came out backwards, and I claim the reason the sign of the Hall coefficient came out backwards is because in some material, the thing that's carrying the current is the holes, not the electrons. Now, you might naively think that, wait a second, this is sort of a trick of bookkeeping. Why should it be that keeping track of an absence of an electron rather than keeping track of an electron should change the Hall coefficient? I mean, underneath, it's all electrons, isn't it? You could always just describe it in terms of electrons if you wanted to. But the key here is to realize that a filled band, a completely filled band, is completely inert and carries no current at all. That's the surprising thing. A filled band carries no current at all. And because of that, you can remove a particle from that band. Then you have a positive charge carrier, so the difference from the inert band that does nothing is now a positive charge carrier. Okay, so we now have simple dynamics of this positive charge carrier sitting at the top of our valence band. Now, so you can certainly dope a material with electrons, like silicon doped with phosphorus, and you'll get a negative Hall coefficient, or you can dope it with boron, and you'll get a positive Hall coefficient. But for various types of metals, let's see if I can find this, we also found that the varying signs of the Hall coefficient, right there, it's right up top. Maybe, it's not there. Oh no, here it is. Yeah. But the various types of metals, we found varying signs of the Hall coefficient, and there were no dopants at all. It was pure metal. Well, the cases that we had were where the Hall coefficient came out with the wrong sign were magnesium and beryllium, which have 2 electrons per unit cell. Actually, I can go back up to the these two. They both have 2 electrons per atom. They're diband, and you would think that it would be a filled band, but it's not a filled band because the bands overlap. It's just like calcium. The bands overlap in the case of magnesium and beryllium, which means that you have both electrons and holes running around. And what decides the sign of the Hall coefficient turns out to be the ratio between the effective masses and relative ratio of the effective masses and the scattering times for the holes and the electrons respectively. So it turns out actually beryllium and magnesium have a positive Hall coefficient, but calcium has a negative Hall coefficient, just because the effective masses come out different in those cases. All right, one more thing that we have to discuss today before declaring the weekend is I promised you that this extra charge, this phosphorus charge thing here, that's incorporated into the silicon lattice, that doesn't do much. It's not that important. So why not? You would think that I have this electron running around, this free electron this electron in the conduction band running around, and it should be attracted back to this phosphorus atom and maybe form a hydrogenic orbital. It's a positive nucleus and a negative electron running around it should form a hydrogen atom, right? Well, it's like a hydrogen atom. So impurities are like hydrogen atom. But 2 main differences. Difference 1 is m star, the effective mass, not the bare mass. Okay, m star, not m. The second main difference, probably just as important, is the Coulomb interaction is e squared over 4 pi epsilon naught, epsilon relative distance between r, rather than e squared over 4 pi epsilon naught r. So there's an epsilon relative, and I gather you studied these last year in E&M. epsilon relative for most semiconductors and some insulators can be frequently around 10, substantial number, so the Coulomb interaction is much weaker, and the effective mass is typically smaller than the bare mass of an electron. As a result, the binding energy, well, you remember in the hydrogen atom, the binding energy is the Rydberg. Rydberg equals, what is it? It's mass of the electron e to the fourth over 8 epsilon naught squared h squared, about 13.6 eV. Whereas here, this is phosphorus atom in silicon, or maybe electron phosphorus atom in silicon. The Rydberg is now m star e to the fourth over 8 epsilon naught times epsilon relative squared h squared, which is about 0.04 eV. Much smaller. So it's a very small binding energy. So the electron is only very weakly bound to this phosphorus atom. So you can draw a diagram, if you like, these are our bands. And if I electron dope this, I put electrons up in the conduction band, but they get bound just below the conduction band in an impurity state. So the very small energy below the conduction band, they get bound to this phosphorus atom and form a bound state. Now, at any reasonable temperature, like room temperature, that electron can get excited out of the impurity state and back up to the conduction band. And that's why I was saying that this positive phosphorus charge really doesn't do much. It actually, the electron breaks free from it at reasonable temperatures and then runs around the conduction band, and this positive charge is then just some disorder that the electron will experience where it comes nearby. At low enough temperature, the electron will get bound again to the phosphorus atom and get stuck, and you'll see the apparent number of electrons in your system will drop as the electrons get bound again to their donors. Similarly, for boron, in the case of boron, you would have a whole impurity state here, state on p dopant, which again has exactly the same properties. That the whole sits up here on the impurity state. At any finite temperature, the whole can get excited down into the valence band. Remember, it takes energy to push the whole down into the valence band. And so you can think of these dopants as just adding, at any reasonable temperature, as just adding either holes to the valence band or electrons to the conduction band. But at low enough temperature, these things will get bound onto the impurities they created in the first place. One more comment about these impurity states is that you can similarly calculate the effective Bohr radius, A Bohr, of these hydrogenic orbitals is analogies to hydrogenic orbital, and the expression for the Bohr radius, if you remember, looks something like this: 4 pi epsilon naught epsilon r. So it differs from the usual Bohr radius by a factor of the relative dielectric constant and by a change in the effective mass. And this number can be 50 to 100 angstroms. So it's a great big orbit that runs around many atoms. It's sort of very weakly bound to this phosphorus atom, or boron atom, it happens to be a hole. Okay, so next time we'll start up again and talk a little bit more about semiconductor physics. We're coming down to the wire. Have a good weekend. Hang in there. 2 weeks to go. Almost there.